design a low pass filter using Butterworth and Chebyshev. Now we'll see how to design an high pass filter. Okay, so first the question is for the given specifications. So specification is alpha p is equal to 3 decibels, alpha s is equal to 15 decibels, and omega p is equal to 1000 radians per second. Okay, 1000 radians per second, and omega s is equal to 500 radians per second. Okay, so this is design a high pass filter. Design a high pass filter. Okay, so for the high pass filter, okay, for the high pass filter, the specifications are given. So the pass band frequency is 1000 radians per second. This is what we have to design. Okay, so and omega is equal to 500 radians per second. Okay, so how we are going to design about is, first we'll draw the response characteristic of a high pass filter. So high pass filter frequency response, something looks like this. Okay, so for low frequencies it is not going to pass, for high frequencies it is going to pass. Okay, so from the question, this is my omega p. Omega p is this is my omega p, and this is going to be by omega s. Okay, so for my high pass filter, okay, so it is going to pass from 1000 hertz. Omega p is 1000, so this is omega s, this is omega p, this is 1000 radians per second. Okay, and this is omega s is 500 radians per second is given in the question. Okay, and this corresponds to 15 dB, minus 15 dB, and this corresponds to minus 3 dB. Okay, this is what is given in the question. And what we need to do for that, first we need to design a low pass filter. We have to design a normalized low pass filter and then convert that into an high pass filter. Okay, so we'll take the same thing, we're going to just reverse it. So this is my 3 decibels and this is my 15 decibels. Okay, so corresponding to 3 decibels we are going to reverse it. So omega p in this case it is 500 radians per second, and omega s in this case is 1000 radians per second. Okay, so this is my low pass filter characteristics and this is my high pass filter. So high pass filter is given. So first we are going to design a low pass filter, normalized low pass filter, and then you have to transform into an high pass filter. Okay, so we'll see. So so what we'll do is that we'll take up the specification is for now is omega p is equal to 500 radians per second, and omega s is 1000 radians per second, and the corresponding alpha p is equal to 3 decibels and corresponding alpha s is 15 decibels. Okay, so we'll take up a Butterworth filter. Okay, we'll directly take up a Butterworth filter. So we can use a formula. N should, so for step 1 is you have to calculate the n should be greater than or equal to log of square root of 10 power 0.1 alpha s minus 1 divided by 10 power 0.1 alpha p minus 1 divided by log of omega c by omega p. Okay, so substituting the values, so square root of alpha s is given as 15. Okay, 15 dB, so it is 10 power 1.5 minus 1 divided by 10 power 0.3 minus 1 divided by log of omega c is 1000 radians per second, and this is 500 radians per second. So from this we can calculate n is actually it comes to perfectly around 2.468. Okay, so we can round it off to the next highest integer n equal to 3. Okay, now we'll move on to the step 2. We have calculated the order. Okay, so based on the order we have to find the poles. Okay, so to find the poles, in our case n equal to 3. Okay, so n is given as 3, so we'll be using the formula sk equal to e power j 5k. Okay, again we have to calculate phi 1. Phi 1 is pi by 2 plus 2k minus 1 into pi by 2n. Okay, so 5k is pi by 2 plus 2k minus 1 into pi by 2n. Okay, so n is so if you substitute k equal to 1, you're going to get pi by 6. So pi by 6 is nothing but 4 pi by 6 or 2 pi by 3. Okay, 2 pi by 3. Similarly phi 2 is going to be pi by 2 plus, okay, so it is 3 pi by 6, so which gives you 6 pi by 6, or you can put it as pi, and phi 3 is equal to pi by 2 plus 5 pi by 6, which actually comes to 8 pi by 6, which we can reduce it to 4 pi by 3. Okay, now we have phi 1, phi 2, phi 3, so we can calculate s1, s2, s3. s1 is e power j, phi 1 is 2 pi by 3, e power j 2 pi by 3. Okay, so it is cos 2 pi by 3 plus sine, so it becomes minus 0.5 plus 0.866 j. s2 is equal to e power j pi, so it is minus 1. s3 is equal to e power j 4 pi by 3, which comes to minus 0.5 minus 0.866 j. So you can calculate the poles. Okay, these are the poles. Once we know the poles, we can find. So step 2 was calculating the poles. Okay, so step 3 was finding the denominator polynomial. So we can find the denominator polynomial as, so one root is s plus 1 into, okay, so it is s minus 0.5 plus minus is here 0.866 j, and another root is s minus 0.5 minus 0.866 j. Okay, so if you go further, d of s is equal to, if you multiply it, okay, if you multiply it, you will be getting it as s square plus s plus 1. Okay, so this is my denominator polynomial. So we can find the h of s. H of s is equal to 1 by s plus 1 into s square plus s plus 1, and we all know that this is a normalized transfer function with omega c is equal to 1 radians per second. Okay, so what we want to do, we want to convert this into a high pass filter. So see here, for the high pass filter, the cutoff frequency is actually, okay, so I mentioned it wrong here, the cutoff frequency is 1000 radians per second. Okay, so this is for high pass. Okay, so we wanted to design it for a sorry, this is omega s, the previous one. Okay, so for the high pass filter it is 1000 radians per second. For high pass filter it is a 1000 radians per second is our desired frequency. Okay, so what we need to do is to convert a normalized low pass filter into an high pass filter. We have to use the transformation as omega c by s. So omega c here in this case is 1000 radians per second. That is the desired radians per second we have to design for. Okay, so 1000 by s. So in the h of s, substitute Okay, so our transfer function here, I'll use a different notation, h of s, and substitute s is equal to 1000 by s. Okay, you remember previously for converting normalized low pass into low pass, we use the transformation as s by omega c. For high pass it is omega c by s. Okay, so now my ha of s, you can find it out as, I'll write the transfer function of the original one. Okay, so s plus 1 into s square plus s plus 1, we have to substitute s as 1000 by s. Okay, so if you substitute it here, so it becomes 1000 by s plus 1 into 1000 by s whole square plus 1000 by s plus 1. So if you solve for it, so the numerator will go into s cube, so it is s plus 1000 into s square plus 1000s plus so here will get, I'll keep the 1000 square as such.